Okay, we're going to go over the conservation of energy practice questions. These are actually really easy questions, but they'll give us the opportunity to get the hang of using the equations in their most basic form. For some of these, it might be tempting to use some kinematics. I'm going to say don't, just for the sake of getting the practice that we need in this new unit. All right, so here we go. Number one, a 200 kilogram boulder is 1,000 meters above the ground. I'm going to read into it that it's actually stationary at the very start. It didn't explicitly say that, but it's kind of hinted at a bit later in part C when it says the boulder begins to fall later. So it's initially stationary, sitting up at the high point of 1,000 meters. To get started, I'm going to make note that I am told that the mass of the object, there we go, the mass of the object is 200 kilograms. It's at a starting height of 1,000 meters. And yes, I'm using the height of the ground itself as kind of the reference point. So measuring up from the ground gives me a positive height of 1,000 meters to start with. I'm also going to record that it's stationary, so speed is equal to 0, just to be clear. It's initially not moving. Okay, part A. Part A asks, what is the potential energy when it's up there? So this is really just a straightforward application of the equation. So U gravity is equal to the unknown. The equation is U gravity equal to mgh, and we have all of the values that we need. So 200 times 9.8 times 1,000. All right, so I've got a calculator on hand, so let's see here. 200 times 9.8 times 1,000 gives me a value that I'll put in scientific notation of 1.96 times 10 to the, that should be what, 6, I think? 3, 4, 5, yeah, 6. And potential energy, as with all energy, is measured in joules. So 1.96 million joules for part A. Okay, moving on to part B. The question is, what's the kinetic energy when it's 1,000 meters above the ground? Well, based on the fact that it's stationary, the answer should be clearly 0, but let's show our work clearly. The kinetic energy is what we're looking for. Kinetic energy is calculated based on speed, 1/2 mv squared, which is 0. There's no kinetic energy initially because it's stationary. Moving on to part C. The boulder begins to fall. What is its potential energy when it's 500 meters above the ground? Okay, now since I started off with an h of 1,000 meters, just to kind of go back to here, I'm going to record this as a kind of an updated height. And I'm going to use the prime notation. So rather than say height initial is 1,000 and a height final is 500, I'm leaving h the way I recorded it earlier, just 1,000 meters. And in particular, I want to point out the absence of a prime mark, that little tick mark, which basically means the initial value. So here I'm going to say the height prime, kind of like an updated value, is now 500 meters. And the question in part C, just to make sure I'm remembering this right, what is the potential energy when it's there? Okay, so U gravity prime is what we're looking for, an updated value. So it's really just a repeat of part A, just using the updated value for height. The new gravitational potential energy is mgh prime, which is 200 times 9.8 times 500. And since the height is half what it used to be, it should make sense that the answer is now going to be half of what it was. So 9.8 times 10 to the 5 joules. Half of what it was. That's it for part C. Part D says, where did the lost potential energy go? So conservation of energy is a big idea. If you lose one form of energy, it means that you've acquired some other form of energy. So in part D, it's really just a recognition question of realizing that, well, this thing's now moving. And because of that motion, it has kinetic energy. It got that kinetic energy from the lost potential energy. So it basically, I'm just going to say it, it gained kinetic energy. So that's where that missing potential energy is. It's not really missing energy at all. Part E. What is the kinetic energy of the boulder when it has fallen 500 meters? Well, it's a very straightforward question, but I'm going to write it up kind of formally, just so that we can rely on this process in the future. So the question is, what is the kinetic energy now? Well, we know the starting potential energy and kinetic energy, and we know the potential energy that it has now. So what we can do is we can rely on conservation of energy. The conservation of energy says that the total energy, mechanical energy, that you end up with better be equal to the total mechanical energy that you started with, allowing for the possibility that maybe there were non-conservative forces doing work along the way. This is something that will show up in a little bit, but for now, hang on to that. There's no non-conservative forces doing work here, so done. The only force was gravity, and that is a very special force. It's a conservative force. Mechanical energy prime and mechanical energy without the prime both mean the total of kinetic energy and potential energy. So on the left side of the equation, I'm going to write the kinetic energy we ended with plus the gravitational potential energy we ended with. And on the right side of the equation, I'm going to write the same thing for the starting point. The kinetic energy we started with plus the gravitational potential energy we started with. There was no non-conservative forces, so the work is already out of there. And as you can see, I know 3 out of 4 of these things. The kinetic energy we end with is the kinetic energy we started with plus the gravitational potential energy minus the gravitational potential energy that we ended up with. I might as well make my life a little easier by saying that the kinetic energy itself was 0, so no point in dragging that any further. That means the kinetic energy that we have now is equal to the starting gravitational potential energy, which was my answer from part A, 1.96 million. Let's see, 1.96 million joules, subtracting the amount that I still have as potential energy, which was my answer to part C, 9.8 times 10 to the 5. And since that was half, it should make sense that the kinetic energy we have now is the other half, 9.8 times 10 to the 5 joules. That's how much kinetic energy we have now. Okay, so part F. What is the kinetic energy of the boulder just before it hits the ground? I'm going to repeat my part E work, but this time I'm going to think of the hitting the ground, or just the moment before you hit the ground, as a double prime moment. So without a prime, like here, I have the initial point where it was initially at rest 1,000 meters above the ground. Here's when it was 500 meters. I'm going to introduce a double prime as a ending point just before it hit the ground. So part F, there we go. Part F, which said, what's the kinetic energy just before it hits the ground? So check this out. The mechanical energy that you end up with is equal to the mechanical energy you started with, plus the net work done by non-conservative forces. And once again, there was none of that. This means that the kinetic energy you end with plus the gravitational potential energy you end with is equal to the kinetic energy you started with plus the gravitational potential energy that you started with. And this simplifies quite a bit too. We know that for part F, we made it all the way down to the ground, so our height is 0. And we also know that we started from rest, so there was no kinetic energy. Oh, there we go. Get that pen back. There's no kinetic energy. What that means is the kinetic energy that we end up with, this is just before we hit the ground, is equal to the gravitational potential energy that we started with at the very, very beginning. And we already know that. Oop, I'll switch back to my blue. We already know that was our answer to part A, 1.96 million joules. 1.96 million joules. So that's really it for part F. Part G, one last part, says, well, how fast is it going now that it has made it all the way down to the ground but not yet hit it, so it still has that kinetic energy. Well, now that we know the kinetic energy is 1.96 times 10 to the 6, I should slip my units in here of joules, we can calculate how fast it must be going. So how fast is it now going? We know the kinetic energy, we know the mass, so we can use our kinetic energy equation as 1/2 mv double prime squared. And by the way, once you start using these primes and double primes, it really starts to make a lot of sense, and it's not at all confusing. If you're thrown by the primes and double primes right now, try not to be. Each prime or double prime, or even the absence of a prime, just marks one key moment in the problem. So double prime is just before impact with the ground. Since I know the kinetic energy and the mass, I can solve for the speed to be the square root of twice the kinetic energy over the mass. So this is equal to, There we go. I keep losing my pen there. This is equal to square root of twice the 1.96 times 10 to the 6 over the mass of, what was it, I think 200 kilograms in the square root. So let me calculate that. Square root of the following, 2 times 1.96, 10 to the 6, divided by 200, close my square root, 140. V double prime is 140 meters per second. And that's it for number 1.